In this lecture, I will discuss process management. I will discuss process context, context switches, and process scheduling. Each process running on a system has a certain amount of information associated with it. A minimal set of state information that allows a process to be stopped and later restarted is called process context. Process context includes the current contents of CPU registers, the current program counter value for the process, and the contents of RAM that the process is using. Switching between processes on a system is often called a context switch, although process switch is a more precise term. The operating system can perform a context switch from a process into a section of the kernel and then back to the same process without actually performing a process switch. Context switches require at least one mode switch to perform, since the CPU must enter supervisor mode to enter the kernel. Relatively speaking, context switches are a fairly expensive operation, and frequent context switching will reduce system performance. Whenever the operating system needs to switch from one process to another, it must first make a context switch into the kernel. The kernel then saves the state of the previously running process and restores the state of the process to which it is switching. A second context switch is then required to start the newly restored process. On Unix systems, processes are created via the fork system call. Following creation, the CPU scheduler determines when and where the process will be run. Once a CPU core is selected, the dispatcher starts the process. Whenever a process makes an I/O request, a system call into the kernel is made, which removes the process from execution while waiting for the I/O to complete. The process yields any CPU cores it is currently using, so that another process can use those resources while the first process waits on the relatively slow I/O device. Operations that cause the process to yield the CPU cores and wait for some external event to occur are called blocking operations. Reading data from a file is an example of such an operation. The process calls the read function, and the read function does not return until it has read some data. The process may have been moved off the CPU and then restored and returned to the CPU while waiting for the read function to return. Some processes are CPU bound, which means they perform large computations with few I/O requests or other blocking operations. In order to enable the system to service other processes and effectively implement multiprogramming, the CPU scheduler must preempt these types of processes. Preemption involuntarily saves the process state, removes the process from execution, and allows another process to run. Interrupts from hardware devices may also preempt running processes in favor of kernel interrupt handlers. Without this type of preemption, the system would appear to be unresponsive to user input. Now, in order to store process state information, the operating system must maintain data structures about each process. These structures are called process control blocks, or PCBs. PCBs contain fields where information about a process can be saved whenever a process is moved off the CPU. Once again, this information includes the contents of CPU registers and current program counter value. The operating system stores process control blocks in linked list structures within kernel memory space. Here is a process control block in greater detail. Some of the information fields include process state, the unique ID for the process program counter, CPU register contents, memory limits for regions of memory used by the process, open file descriptors, and other data. When performing a process switch, it is critical that the operating system saves the process's CPU state. At a theoretical minimum, this state information includes the program counter and CPU register contents. In practice, more information will be saved during each process switch. This diagram presents a simplified view of process switching, where only the program counter and register contents are saved and restored. Here, the operating system switches from the process with ID 1 to the process with ID 2. The first step in the process switch is to perform a mode switch into kernel mode, along with a context switch to the section of the kernel that handles process switching. That component of the kernel saves the program counter and CPU registers into the process control block for process 1. Also, the process state for process 1 is set to ready, indicating that the process is ready to run again once the CPU core becomes available. The process switching code then restores the CPU register contents and program counter value from the process control block for process 2. The state of process 2 is changed from ready to running, the CPU privilege level is returned to user mode, and context is switched to process 2. Process 2 now begins executing. During the lifetime of a process, the corresponding process control block is moved between various queues in the operating system. Each queue is a linked list of process control blocks, and multiple linked lists overlap. All PCBs are at all times in the job queue, which is a linked list of all process control blocks in the system. Process control blocks corresponding to processes in the ready state are linked into the ready list. Processes waiting for device I/O have their PCBs linked into various different device queues. In this diagram, we can see the PCBs for 5 different processes. All PCBs are members of the job list, with list links depicted by the green arrows. 3 jobs are in the ready list, and 2 jobs are in a device queue waiting on I/O. The linked lists within each queue are represented by the dark blue arrows. Notice that the 2 linked lists for the queues overlap the linked list for the job list. Careful management of linked lists is a major requirement of operating system kernel code. Now I'd like to shift focus for a moment to mention scheduling, since it is closely related to the linked list management. In operating systems theory, we typically divide scheduling into 3 types: job scheduling, midterm scheduling, and CPU scheduling. Job, or long-term scheduling, refers to the selection of processes to place into the ready state. This type of scheduler has a long interval, typically on the order of seconds to minutes. One of the clearest examples of job scheduling on modern systems occurs on high-performance computational clusters, on which users submit jobs that may require hours to be scheduled and execute. Midterm scheduling refers to the swapping of inactive processes out to disk and restoring swapped processes from disk. Many of these tasks are now part of the virtual memory subsystem. CPU scheduling, or short-term scheduling, refers to the selection of processes from the ready list to run on CPU cores. This type of scheduling will be the subject of future lectures. One important operating system component related to short-term scheduling is the dispatcher, which receives a process control block from the short-term scheduler and restores the context of the process. The dispatcher also completes the context switch to the process by performing a mode switch into user mode and jumping to the instruction address specified by the newly restored program counter.